When the music's over, when the music's over, yeah. When the music's over, turn off the light, turn off the light, turn off the light. Yeah, yeah. When the music's over, when the music's over, when the music's over, turn up the light, turn up the light, turn up the light. What the music is your special friend. Stay on fire if you dance. Music is your only friend. Until the end, until the end, until the end. Cancel my subscription to the resurrection. Send my credentials to the house of detention. I got some friends inside.
Morning.
The face in the mirror won't stop. The girl in the window won't drop. A feast of friends, alive she cried, waiting for me outside. Before I sank into the big sleep, I want to hear the scream of the butterfly. Come back, baby, back into my arms. We're getting tired of hanging around. Waiting around with our heads to the ground. I hear a very gentle sound. Very near yet very far. Very soft yet very clear. Come today, babe, come today. What have they done to the earth? What have they done to our fair sister? Rabbits and plundered, richer and bitter. Stuck her with knives in the side of the dawn and tied her with fences and dragged her down. I hear a very gentle sound. With your ear down to the ground. We want the world and we want it now. Right, Mama? Now. Well, you might see a light, save us, save us. So when the music's over, when the music's over, yeah. When the music's over, turn up the light, turn up the light, turn up the light. When the music is your special friend, it's on fire, easy and tense, he's your only friend. Till the end, until the end, until the end.
All right. Morning, everyone. How are you doing? So I'm trying to go through the questions one by one. This was the first one. Zoe was asking for suggestions. I don't have many suggestions as to how to tackle things in general. You just have to adapt. I think you'll find the final is very straightforward, so not much adaptation is required. Can you tear off scrap paper at the back? You're not supposed to tear anything out. So you see the idea, right? I mean, you have this person running on a track with a friend sitting 200 meters from the center, and the guy is running at 7 meters per second or something to that effect. That is actually the rate of change of the length, right? If you think of it as an arc length, right? So using the law of cosines, which I don't expect you to know by heart. So if you absolutely need it for a certain question, it will be supplied. If you don't need it, then it will not. So you see this law of cosine relates the distance and the angle. So if we knew what d theta dt actually was, you'd be good to go. But we're given that the rate of change of the arc length is 7. So is there a relationship between the arc length and theta? Well, you know the circumference of a circle is 2 pi r. Or in this case, 2 pi times 100. Well, let me leave it as r. It's nice to do it in general. So 2 pi r. Here, right, so that's the length of the whole thing. You don't have the whole thing here. You only have a fraction of the circle. What fraction? Theta over 2 pi. Right? If theta was 2 pi, you would have the whole thing. You don't. You only have a fraction. What fraction? Theta over 2 pi. So the arc length, L, viewed as a fraction of the whole circumference, is really r theta. Very nice. Where r is 100 here. So you see that dl dt is 100 d theta dt. And you can finish that up. Very nice. Gabriel else wants to consider intervals of increase and decrease for x 10x. Let's do it. First of all, this being sine over cos, you want to stay away from odd multiples of pi over 2. I suspect that this question had restricted the domain to minus pi over 2 and pi over 2, if I remember correctly. So there it is. So take the derivative. And if you differentiate, I mean, if this question had not restricted the domain, then the domain would have been everything except multiples, odd multiples of pi over 2. The derivative, 10x plus x secant squared, which is sine over cos, plus x over cos squared. Common denominator gives us sine x cos x. Over that. So if, and it's a big if we are restricting our attention to that domain, I realize that I'm not going to be able to see questions coming up, so I'll have to be scrolling up and down. If we're restricting our attention to that domain, critical points are where the denominator is 0, right, where the derivative does not exist, and this denominator is 0 precisely at those points, which are not in the domain, so no critical points from there. And the numerator, well, the numerator, that's not very clear, right? So let's investigate the numerator by looking at this. Question arises, is this ever 0? And if so, where? Well, just by inspection, you may have noticed a root, right? When x is 0, sine is 0, and that is 0. So at 0, the function is 0. Question arises, are there other places where the function is 0? It's not clear. There could be. So let's investigate. Let's look at the derivative. Derivative of this is what? Cos x, cos squared, right? It means the product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Derivative of cos is negative sine. Derivative of x is 1. You may recognize a half-angle identity for this. This is really cosine of 2x. And what do we know? We know that cosine of theta is between -1 and 1. So cosine of 2x is between -1 and 1. And when you add 1, cosine of 2x is always bigger than or equal to 0. What does that mean? Well, that means, right, that's your derivative. Your derivative is always bigger than or equal to 0. What does that mean? If the derivative is always bigger than or equal to 0, then the function is increasing. Consequently, if it crosses the x-axis, it never comes back down to cross it again. Conclusion, there's only one critical point at 0. At 0, which is in here, if your domain was everything except all multiples of pi, the answer would still be the same. Right? Your function only has one critical point at 0. So if you draw a, sorry, not f anymore, but y prime, if you draw a domain, again, if we're restricting our attention to this, that's fine. Otherwise, there would have been no critical points in the other intervals. So you would have continued 3 pi over 2, 5 pi over 2, and so on. And plug in. If you plug in a value very close to 0, but negative into here, cosine is positive, sine is negative, and this is negative. So the whole numerator is negative. Denominator is always positive, so the whole thing is negative. And a value bigger than 0, everything's positive. There it is. Scott is asking why 0 is a critical point, but I mean, sorry, what have I done here? This is the derivative, not y. So this is the derivative, and we were getting critical points from the derivative, right? So where the denominator is 0 or the numerator is 0. So we had to look at it differently. Would Rolle's theorem also apply in this case? I mean, the problem with Rolle's theorem, especially if you're using this whole interval, is that this could be 0, right? This is going to be 0 at, where is it 0? It's actually 0 at places not in the domain. So Rolle's theorem would be fine here as well. Absolutely. Why did you take the derivative of the top again? Well, I mean, I don't know. We're looking for when this is 0. And I cannot solve for that. And thank you. I cannot solve for that. And we have to be able to answer the question some other way, which is exactly what we did. Can't you say 0? I don't know what that means. Yeah. Well, I mean, we did notice that. But my question is, are there other places? I don't have any office hours today, Jackie. My question to you is, when is this 0? Yes, it's 0 at 0. Are there other places? For concavity, Gabrielle, you're going to do the same. Exactly. All right. Let me go back. Paul was asking. Determine f prime of 0. So f of x is defined to be x sine 1 over x for x not equal to 0. And 0 when x is 0. The question is, what does f prime of 0 exist? That's the question. And the answer will be no. Let's do it. F prime of 0 is the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. So f of h, when h is not 0, right, but tending to 0, this is h sine of 1 over h. F of 0 is 0 over h. The h's cancel nicely, leaving you with the limit of sine 1 over h. And as h goes to 0, this stuff goes to positive infinity or negative infinity, depending on which side you're at. And you know what's happening to sine. Sine just keeps oscillating forever. This limit does not exist. If this argument is not sufficient for you, take some very small values of h. Right? Take very small values of h very close to 0. What am I referring to? Values 1 over n pi. If you take a very large n, for large n, h is going to be close to 0. And what is sine of 1 over h? This is sine of 1 over n pi. 1 over n pi is sine of n pi, which you know to be 0. So for these values, which are very close to 0, the function is 0. But now, consider Consider 1 over 2n plus 1 pi over 2. Again, for large values of n, this denominator is very big, and so h is close to 0. Yeah, that is not what I want. That is not. Yeah, no, it is what I want. So for large n, h is close to 0. And sine of 1 over h is sine of 1 over 2n plus 1 pi over 2, which is really sine of 2n plus 1 pi over 2. So odd multiples of sine is either going to be plus or minus 1, depending on what n is. It's actually what? Negative 1 to the n plus 1. Right? If n is 0, if n is 0, we're looking at sine of pi over 2, which is positive 1. When n is 1, this is sine of 3 pi over 2, which is negative 1. When n is 2, it's sine of 5 pi over 2, which is positive 1, and so on and so on. So you see, what's my point here? If you take some small values of h, sine is going to be 0, and at other small values of h, close to 0, sine is either positive 1 or negative 1. It doesn't approach a unique limit. The limit does not exist. Couldn't you, Zoe was asking if we could use a squeeze theorem here? No. No squeeze theorem, because all you can say is that sine is between negative 1 and 1. So there's nothing that's going to bring everything down to 0. Right? I mean, we had an example like this on the midterm, where we had x squared instead. It was x squared cosine, but it's the same thing. And that worked. That had a derivative of 0 at 0. Moving on. If h of x is 2 sine x minus secant squared, find the antiderivative. So really, this is how you would expect the answer to be, the question to be posed on the final. What is the antiderivative of 2 sine x minus secant squared dx, right? This dx is just notation. Don't let that worry you. And what do we expect as an answer here? Antiderivative of sine. What function has derivative sine? You know that to be negative cos. Antiderivative of secant squared. What function has derivative secant squared? You know what it is. It's tangent. Throw in your arbitrary constant, and you're done. Somebody's suggesting that the question is, the answer supplied is breaking up into an appropriate interval, an appropriate domain. You don't have to worry about that. Let's not worry about the domain here for the antiderivative. Should we know the principle of similar triangles? Andrew is asking. I never called it the principle of similar triangles. Rather, I suggested, we've been using that over and over again. Instead of similar triangles, I'm always calculating tangent of some angle. So whatever you want to call it, it's fine. And so short answer, yes. We've been using it over and over again. So Alyssa is asking for the limit as x goes to 0 from the right of arctan 1 over x. As x goes to 0 from the right, 1 over x goes to infinity. So really the question is, what is arctan of infinity? And if you don't know what that is, call it theta, and this is equivalent to asking for what value of theta is tangent of theta equal to infinity. So you know the graph of tangent. The question is, when does tangent blow up? And it blows up at pi over 2. Well, you're thinking to yourself, maybe you're thinking to yourself, it also blows up at 3 pi over 2 and at 5 pi over 2 and so on. Aren't those values to be used as well? But you know that with the arctan, it's understood that you're restricting your attention to the interval minus pi over 2 to pi over 2. So this is pi over 2. Similarly, limit as x goes to pi from the negative of the ln of sine. What is happening to sine as you're going to pi from the left? Well, you know the graph of sine. Here's pi. So as you go to pi from the left, sine is going towards 0 from numbers bigger than 0. And that's important in order for this to be defined, because you know ln is not defined for negative numbers. So this is going to 0 from numbers that are bigger than 0. And what is happening to ln as x goes to 0 from numbers bigger than 0? You know ln is going to negative infinity. There it is. Sod wants the largest rectangle inscribed in a circle. Radius r. Right, this is the drawing where the vertices are on the circle. So these vertices are on the circle. The x and y values satisfy this equation. Right, so this is your x here, and this is your y. So this side has length 2x, and that side has length 2y. The area is 2x times 2y, or 4xy. I think we did this question before. Pretty sure we did this question. Well, I mean, I know we did it with, let's say this. We did it with an ellipse, right? X squared over a squared plus y squared over b squared is equal to 1. So since we did it with this, take a and b to be r, and boom, you're in the circle situation. So in the interest of time, let's not redo it because it's already done. Look it up and take a and b to be r, and that will answer your question. Somebody wants to do some questions with oblique asymptotes. Do we have to know the law of cosines? You don't have to know it by heart. If you can do a question without it, it will not be supplied. If you absolutely need it for a question, it will be supplied. So let's say that. We want to do some oblique asymptotes. Somebody's at, so oblique asymptotes. Why don't I start you off with an example. X squared plus 3x minus 1 over x plus 2. Work that out. Thiara is asking, when finding the derivatives of inverse functions, can we use implicit differentiation and not the textbook formula? Certainly you can. Find the point on the line that is closest to the origin is a question Sarah's asking. I believe we did that exact question last time. No, sorry, I did it in my office hours with somebody. So we'll do it. We'll do it after. Lynn was asking what was the song. It was When the Music's Over by The Doors. Priya's asking, when using the slant asymptote, can we do it using long division, or do we have to do it the mx plus b method? Either way, we will accept either way. I mean, you're going to want to justify that it is a slant asymptote, right? So you're thinking to yourself, we're going to divide, and let's do it. So x minus 1, leaving us with a remainder of minus 3. So in other words, this can be rewritten as x plus 1 minus 3 over x plus 2. Well, so this is the way to do it using long division, right? You rewrite this in this way, and then you're thinking to yourself, if this wasn't there, as x goes to infinity or negative infinity, this goes to 0, right? Limit as x goes to infinity of your function minus x plus 1, right? These cancel out nicely, and you're left with this business. Which is easily seen to be 0. And that's the definition. That's the definition of a slant asymptote, right? Your function minus mx plus b equal to 0. Well, limit as x goes to infinity. And similarly, and that does it. But, you always have to go back to the definition, right? So here you don't have to solve for mx plus b because it's really obvious. And there it is. Now, somebody was asking, what if you don't have a denominator? Well, of course, if you don't have a denominator, then this is not going to work out. Zoe's asking to do it using the mx plus b method, and let's do it. Exactly, as Kylie suggests, you need to show the limit as x goes to infinity and or negative infinity is 0 when you subtract it, because that's really the definition of an oblique asymptote, right? The definition is that this should be 0. So put everything over common denominator. And remember, we're forcing this to be 0. Let's group the powers of x. So this is 1 minus mx squared, 3 minus b minus 2m x, and minus 1 minus 2b over x plus 2. And as x goes to infinity, now here's where your experience is important. You've done lots of these questions. And take a step back. Look at this business. It's one polynomial divided by another, right? So you certainly are going to have the form infinity over infinity. This is a polynomial of degree 1. This is a polynomial of degree 2. Or rather, I should say, if it is a polynomial of degree 2, then we're in trouble, right? Because if you really do have an x squared here, you're going to differentiate once using L'Hopital's rule, and then you'll still have an x. And what's the limit going to be? You know what the limit's going to be. The limit's going to be some sort of infinity if you have an x squared in here. And you don't want that. You want the limit to be 0. So the only way the limit can be 0 is if you did not have an x squared here. In other words, if the coefficient of x squared was 0. So in order for this limit not to be infinity, we need not to have an x squared, or in other words, the coefficient of x squared should be 0. So m has to be 1. I mean, I've rubbed it off now, but x plus 1 was our slant asymptote here. Notice that m was 1. So if m is 1, in this case, what happens? If m is 1, this is gone. So we're left with 3 minus b minus 2 times x minus 1 minus 2b over x plus 2. And now same argument. Same argument. If you have an x in the numerator, then you're going to have an infinity over infinity. And when you differentiate, well, okay, so maybe 2 ways to go. Either you don't want an x in the numerator, or if you do, when you do a L'Hopital's rule, you end up with a limit of 1 minus b. So in both cases, you need 1 minus b to be 0. Right? In both cases, either the limit is this, it's 1 minus b, which has to be 0, or arguably you don't want an x. So both situations go back to this. In other words, b has to be 1. So in other words, the slant asymptote y equals mx plus b, y equals x plus 1. Exactly the same answer we had before. Now you want to, I mean, it's clear that this whole process will also work as x goes to negative infinity. Can you also find oblique asymptotes to higher degrees with the mx plus b method? I'm not sure what higher degrees refers to. I don't entirely get how there's two options in the last step, but both lead to the same answer, right? Either you're thinking to yourself, the only way this is going to be 0 is if I did not have an x. So you need the coefficient of x to be 0 in the same way that you needed the coefficient of x squared to be 0. Or assume it's there and do a L'Hopital's rule. The derivative will still be the coefficient. I mean, the limit of the derivative is going to be the coefficient, and that has to be 0 again. So both give you the same answer. Two ways to view it, and it's still equivalent. An oblique asymptote of x cubed, that's not going to happen. That's not going to happen because x cubed does not behave like a straight line. Exactly so, you could assume infinity over infinity and do a L'Hopital's rule, and that would force the coefficient to be 0 again. Miriam wants to graph. Y equals the square root of 1 minus x squared over x squared. Let's do it. Maybe Jackie was asking about the office hours for TAs. TAs should have regular office hours. I mean, it is a regular Monday. Let's graph this. Question arises naturally. What is the domain? And first of all, you certainly don't want x to be 0. And also, you're taking a square root. So you want 1 minus x squared to be bigger than or equal to 0, but that factors as 1 minus x, 1 plus x. So when is a product bigger than 0? When both factors are bigger than 0. or both numbers are less than 0. So here we need x less than 1 and simultaneously bigger than -1. So this is the domain -1 to 1. And here you need x bigger than 1 and simultaneously less than -1. And that never happens. There are no numbers which are both bigger than 1 and simultaneously less than -1. Consequently, the domain is -1 to 0, union 0 to 1. Let's move on to the derivative. This is a quotient, so quotient rule applies. VU prime minus U V prime all over V squared. Let's cancel the 2 here. Let's factor out an x square root of 1 minus x squared from the numerator. No, I don't want to factor that out. I want to factor in 1 over square root. So that's taken out. That's taken out. We're left with a negative x squared here. Minus the x is gone. So I have a 2, 1 minus x squared. All over x to the 4, I can cancel one of these. Let's rewrite this as, it's going to be 2x squared minus x squared, so that is x squared minus 2 over x cubed square root of 1 minus x squared. Critical points are easily seen. Let me write them here. This saves. Critical points would have been plus or minus root 2 outside of the domain, 0 outside of the domain, and plus or minus 1, which are actually endpoints, so they're not going to play a major role. Let's draw a first derivative chart. Minus 1, 0 is not in the domain, so there's a break there. Very good. If we plug in a value close to 0 but less than 0, this is negative, this is positive, this is close to 0, so the numerator is going to be negative, 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 positive. The whole thing is positive, your function is increasing. Again, a number close to 0 but just bigger than 0, this is positive, that's close to 0. So numerator is close to -2, negative, positive, positive. The whole thing is negative. There we go. What's happening at 0? Nothing, right? We know it's not in the domain. Let me rewrite the domain here. I forgot x and y intercepts, but I think they're clear. Why don't I write that here? If x is 0, it isn't. And if y is 0, x is easily seen to be plus or minus 1. We have our first derivative chart. Let us evaluate the second derivative. How are we doing here? Thank you, Jacob. going a bit too fast here. Y less than and equal to 0 as well. It doesn't matter, Miriam, right? Whether you had strict inequality or not, if both were equal to 0, you would have had some overlap, and no big deal. Second derivative, let's do it. So V U primed minus U V primed, and V is a product, so product rule applies. 3x squared, leaving that fixed, plus leave the x cubed fixed, differentiate the square root, 1 over 2 square root, times the derivative of the inside, negative 2x. Was I missing a negative here as well? I may have been. No, very good, we're good. Miriam, we broke up 1 minus x squared as the product of two things, right? So when is the product of two numbers bigger than 0? If those two numbers are positive, you get a product that is positive. But if the two numbers were negative as well, right? Negative 3 times negative 2 is positive 6. So the product of two numbers is positive if those two numbers are bigger than or equal to 0, or if those two numbers are less than or equal to 0. All of this over V squared, so x to the 6, 1 minus x squared. All right. What do we want to do? I'm going to suggest factoring out. We have an x squared here. So let's factor out an x squared and a 1 over the square root. I think that's it. So here I still have a 2. I had an x to the 4, so I'm missing an x squared. I factored out this, so I'm left with that. I factored out an x squared. So I still have a 3. I factored out 1 over square root, so 1 minus x squared. Minus. The 2's cancel out nicely. I had an x to the 4. I took 2 out, so I've got an x squared. And I took that business out as well. There we go. All over x to the 6. 1 minus x squared. So you can cancel 2 of these. And you can bring that down. Maybe expand this. Am I missing some brackets? A little bit of algebra involved here, but it's all good. Because we see where this is headed. And let's expand. 2x squared minus 2x to the 4. X squared minus 2 times, let's expand this. This is 3 minus 4x squared. All over x to the 4. 1 minus x squared to the 3 over 2. Eddie's a bit ahead of us. Almost done. Expand this, and we should get Eddie's answer. 3x squared plus 4x to the 4 plus 6 minus 8x squared. Cancels out. Let's look at the x to the 4. So we get a 2x to the 4. The x squared, that's a minus 1. Minus 9. Oh, I think we have a different answer from Eddie. That's oh no, the same. Very nice. Very nice. Perfect. All right. Possible points of inflection. From the denominator, 0, which is not in the domain, plus or minus 1, which are in the domain, but again, they're just at the edge, so they're not going to play a role. And then wherever the numerator is 0. And I'm sure you've noticed. Yeah, you could have that on the final. It's a bit much, but it's just algebra, right? Multiplying polynomials together. I mean, this is high school stuff. When is 2x to the 4 minus 9x squared plus 6 equal to 0? Well, you've recognized this, I'm sure, as a quadratic in x squared. Thank you, Eddie. Let t be x squared. So this becomes 2t squared minus 9t plus 6. And this is a quadratic. Very nice. So quadratic formula, negative b plus or minus square root of b squared minus 4ac minus 48 over 2a. So 9 plus or minus square root of 33, is that right? All right, that's a bit questionable. Certainly, the addition is out, right? Because 9 over 4 is already outside of this interval. So if you add a root 33, it's even larger. So 9 plus root 33 over 4 is outside of the domain. So that's out. What about the negative? What about 9 minus root 33 over 4? This is close to 6. 9 minus 6 is 3. So this is going to be close to 3 over 4. This is probably what did I forget to do? Forgot to square them. Well, I mean, I am just solving for t, right? So this is really for x squared. And then I have to take the square root. But since this is bigger than 1, its square root is also going to be bigger than 1. So we're fine. It's not the square, but it's the square root, right? But here, I'm quite certain, right? Do we want to prove? Well, so if you thought it was a lot of algebra before, now it's a lot of algebra. Probably too much algebra now. So my claim is root 33 is less than root 36, which is bigger than root 25. So it's between 5 and 6. So when you take negative, it's going to be bigger than negative 6 and less than negative 5. And when you add 9 to both sides, 4 is bigger than 9 minus root 33, bigger than 3. And then when you divide by 4 or multiply by 1/4, there it is. So this is some number between 3/4 and 1. Very nice, Eddie. And consequently, when you take the square root, so the square root of that is going to be between 1 and the square root of 3/4. So it is in the domain. That and its negative is going to follow a similar inequality. So plus or minus are both possible points of inflection. So if we draw a second derivative chart, -1, 0 is not there, and 1, and then you have these things, square root of 9 minus root 33 over 4, and it's negative. All right. And now we don't have a calculator. Thank you, Paul. It's nice to have some confirmation. And what? What are we going to do? We're going to take a number very close to -1. Because, you know, I don't want to calculate how close. I don't want to find a number between those two. We're going to take something very close to -1. But just less than -1. When you square it, you get something less than 1. So this is positive. This is to the 4, so that's going to be positive. Well, I mean, you know, here, yeah. Actually, I never have to worry about this because I know 1 minus x squared is always positive. So the denominator is always positive. The sign is going to depend on the numerator. And if I take something close to -1, this is going to be close to 2. That's going to be close to -9. So -9 plus 2 is -7, plus 6 is -1. The numerator is going to be close to -1. So numerator is going to be negative. In other words, your function is concave down. If you take a number very close to 0, but less than 0, again, denominator is positive. This is close to 0. That's close to 0. Numerator is going to be close to 6. So positive. Similarly, if you take a number on the right of 0, just very close to 0, but positive, denominator is always positive. That's going to be close to 0. That's going to be close to 0. So numerator is close to 6 again. So positive. And if you take something very close to 1, this is going to be close to 2. That's close to -9. That's 6. So 2 minus 9 is -7, plus 6 is -1, negative again. So these two things are points of inflection. All right, almost ready to graph. Almost ready to graph. Let's get rid of this. Almost ready to graph. 0 is not in the domain. We would like to know what's going on there. What is happening at 0? Limit as x goes to 0. If you just plug in, you get a 1 over 0, so you know this is some sort of infinity. Is it positive or negative? Numerator is positive. Denominator is positive. Everything is positive. Similarly, here. An excellent question. Is that an even function? Right? Nice to notice before you start graphing. If you plug in -x, this is 1 minus -x all squared over -x all squared, which is 1 minus x squared over x squared, which is the original function. i.e., it's an even function. Very nice. Mariama is asking a good question. Oftentimes, something will suggest a mistake has been made, right? Oftentimes, the work will contradict itself. And I would like you to, well, I mean, so as Maya suggests, I want you to graph the work you did. Don't start with a preconceived notion of what the function looks like. I don't know what that function looks like. We're going to graph what is given. And if the graph doesn't make sense, then you know a mistake has been made. And then you go back and figure out where the mistake is. So if x is plus or minus 1, y is 0, right? So at -1, we're at 0. And at +1, we're at 0. So this is where we're starting. We are increasing concave down all the way to this point. So increasing concave down all the way to that point. At which point we are still increasing, but now concave up all the way to 0. Where's the 0 taking us? As you approach 0 from the left, you're going to positive infinity. So increasing concave up all the way to 0, where you approach positive infinity. After 0, where are we? After 0, you're at infinity. I mean, since you know your function is even, you could have just done a mirror reflection. But let's not even do that, and let's graph the work that's given, and we should notice that there is this symmetry. This will also guarantee that nothing has contradicted itself, right? So after 0, you're starting at infinity, you better be decreasing. And you are. There's nowhere to go but down. Decreasing, concave up, all the way to this point. You know you haven't crossed the x-axis. Right? Because the only x-intercept is going to be at 1 afterwards. This is root 9 minus root 33 over 4. At which point you are still decreasing, but now concave down all the way to 1. There it is. Normally it would be nice to point out the y value. Here it's just a lot of calculation, so let's not worry about that. It's nice to point out that these are points of inflection though. So whenever possible you work it out, but here it seems like it's more trouble than anything. We know it's positive, that's all that really matters. You could skip, as Connor suggests. I advise you not to do that. Rather, graph your function, and then your work really should suggest it's even, and you proved it as well. You could have proven it after. If you hadn't noticed, somebody pointed it out to us, I probably would not have noticed it immediately. But then after graphing, I would have asked myself, oh, this does look like an even function. Is it really? And then you go and prove it. Has the exam been written to take a full 3 hours? I think you can do the exam. I mean, what do I want to say? I did the long answer portion yesterday. It took me an hour to write up solutions, complete detailed solutions and a marking scheme. Took me an hour. The multiple choice is probably shorter. So for sure, you can do everything in 2 hours. Leaving you an hour to go back and giving you an hour to go back, redo some questions, make sure everything is perfect. Gabrielle is asking how we got positive infinity. Plug in 12 multiple choice questions. Yeah, I misplaced the answers for the long answer questions. So Maybe they'll pop up again at some point. Not reflected above the y equals x, but rather the y equals negative x if the function is odd, right? Yeah, so plug in Gabrielle, right? If you plug in, you get a 1 over 0. So you know it's some sort of infinity. The only answer you have to determine is it positive infinity or negative infinity? Here, there's nothing mentioned in front of the square root sign, so it's understood to be the positive square root, and your denominator is something squared. So it's always positive as well. There is a clock in the exam room. It tells you exactly how much time is left. Absolutely. Do we need to consider limits at 0 all the time in this type of question? No. The 0 is not a special number. Here, we considered 0 because 0 is not in the domain. So we have to question what's happening at 0. Why isn't 0 in the domain? You can bring your wristwatch, absolutely. Okay, you're allowed to have a watch, no problem. And he's asking, did we do horizontal asymptotes? We did not, right? Because the domain was limited to -1 to 1. So we don't have to answer the question, what is happening as x gets larger and larger? Because it doesn't, right? It stops at -1 and 1. Do I think the exam will be curved? I don't expect to have to curve. Historically, people do fine on the final. For oblique asymptotes, should we check for them as x goes to infinity and negative infinity if both limits are some kind of infinities? Exactly. Yes, you should. Michael, I've posted a link to the final exam schedule. All the information is there. I believe it's in the gym. I haven't, I think people mentioned that it was as well. Right, you'll see hordes of people walking up university. Just follow the crowd. Oh, look, majority of people do well in this course. So if you've done lots of exercises from the book, there's no reason for you not to do very well on the final. Domain and intercept of ln sine x. You don't want to take ln of a negative number, so sine has to be positive. So graph sine and figure out where it's positive. That's going to be the domain of the ln sine x. Working out a hyperbolic trig function, what does that mean? You want me to find the inverse of a hyperbolic trig? Not all the long questions will take as long as graphing. Absolutely. The graphing, of course, is time consuming. All the other long answer questions are pretty straightforward. 12 multiple choice, 10 long answer. That's exactly it. All right, let's do these last two questions. I don't want to take up too much of your time. I want you to take the remainder of the day to study. If you have specific questions, you can email me. So somebody was asking for the inverse of a hyperbolic trig function, and let's do the inverse hyperbolic tangent is. Only because we did the inverse hyperbolic sine in class, the inverse hyperbolic cosine is going to be the same thing. So let's work this one out. You have y is hyperbolic tangent of x, which is e to the x minus e to the minus x over e to the x plus e to the minus x. And you know how to find the inverse. You interchange x and y. And solve for y. So bring this over, and you get x times e to the y plus e to the minus y. And multiply both sides. To get rid of the negative exponential here, why don't we multiply both sides by e to the y? So you get x e to the 2y plus 1 is equal to e to the 2y plus 1. All right, that is seemingly easier than expected. I never actually worked it out. Expand. So x e to the 2y plus x is e to the 2y plus 1. Let's bring this over. And bring this x over. Factor out an e to the 2y. I feel a mistake has been made. Thank you. -1 on the right-hand side. -1. There we go. -1, right? I mean, I knew a mistake had been made because things were canceling out. Right? This is negative of that, so when you divide, you get -1. So something was off there. Thank you for noticing. Exactly. You don't need to memorize these, but you should be able to work them out. -1 minus x over x minus 1. Take ln on both sides. And y is 1/2 of that. There it is. Yes, seen. How many critical numbers does Will there be proofs of hyperbolic identities on the final? There could. There could be some showing this hyperbolic identity. These are very easy. Free points, essentially. I mean, I keep using critical numbers and critical points interchangeably. The critical number is really the x value, whereas critical points are the xy points. No marginal cost and revenue. All right. So here you're given this derivative in terms of an absolute value. Is always asking if we should say critical number on the exam. It's not going to be an issue. Are we responsible for solving composite inverse trig functions where we have to adjust our answer to match the domain? Possibly. I'm not 100% sure what you mean by that, but it seems like understanding the domain of inverse trig is important. All right. So how many critical numbers? Who knows? Who knows? So first of all, understand that this is defined for all values, all real numbers, right? So the domain of the derivative is all real numbers. And working with absolute value, it's always a bit of a pain. So I'm going to suggest restricting our attention. So, well, here's what I suggest. Get rid of the absolute value. You don't need to memorize the derivative of the inverse hyperbolic functions, nor their derivatives. But I expect you to be able to work them out like we did here. So let's get rid of the absolute value of x. And you know how to do that, right? So we're going to break that up into positive values of x, right? So we're going to answer the question, what are the critical numbers if x is bigger than or equal to 0? For the inverse trig functions, inverse sine is defined only on that interval. If I use the label arcsine x, you know what interval sine was restricted to in order for this to exist. And it's never for any other domain. No half-life and compound interest. So if we let x be positive, in that case, the function is this. You know what? In order to define the inverse cos, we restricted the attention of cosine to the interval 0 to pi, so that we had a one-to-one function. Exactly. All right, so we have this. What do we know? Everything is continuous here, right? Very well behaved, continuous, differentiable, everything is nice. f of 0 is minus 1. And eventually, I mean, I probably shouldn't say that. I don't know. Who knows? Who knows what happens? Nobody knows. Nobody knows. So let's sorry, I've called it f, but it's really f prime. Why don't I change it to g? G is f prime when x is bigger than 0. So let's study G in generality. G of 0 is negative 1, very good. Let's take the derivative, see how G behaves. So 5, this is a product, so product rule applies. Derivative of the first part is this times the derivative of the inside. Plus leave the exponential fixed. Differentiate sine, whose derivative is cos. And if we factor out an exponential out, this is what we get. All right. So the question is, what are the critical points of G? When is, first of all, G prime is defined everywhere. So critical points are going to be where this is 0, right? Because the exponential is never 0. So this is going to be where cosine is 1 over 10 times sine. Or equivalently, where tangent is 10. All right. Where tangent is 10. So this is arctan of 10. But also, you know that tangent is periodic of period pi. So x is arctan of 10 plus multiples of pi. Right? It's going to happen here again. And here again. So this is arctan of 10 plus pi. This is arctan of 10 plus 2 pi, and so on and so on. It's a lot of work, absolutely. Absolutely. And what? Notice, if we look at G a little more closely here, for large values of x, this is going to be very small, very close to 0, which is going to make everything very close to 0. So for large values of x, this is always going to be negative. right? So for large values of x, this is going to be close to 0. So g is going to be negative. And consequently, f will not have any large critical points. But it could have some critical points that are not too large, right? So arctan of 10 plus 2 pi, and so on and so on. So to answer this question well, I think we would need a calculator to figure out how far you have to go in order for this to be less than 1. Probably not that far, right? And then you could draw a first derivative chart for g. Starting at 0, your first critical point is arctan of 10. Second critical point at arctan of 10 plus pi, and so on and so on. And what we want to do is essentially apply an intermediate value theorem argument, right? What's going to happen here? For values close to 0, but positive, this is always positive, so that's not an issue. This is going to be close to 0, and that's close to 1, so your function is increasing. Remember that we started at -1. So really the question is, what happens at arctan of 10? Did you surpass the x-axis? If you did, then there had to be a point between 0 and arctan of 10 where the function was 0, where the derivative was 0. That would have given you a critical point. And then, in this interval, what happens here? Here, sine is going to be bigger than, 1/10 sine is going to be bigger than cosine, so you can take the point pi over 2. Pi over 2 is going to be in between these two. Sine of pi over 2 is 1. Cosine of pi over 2 is 0, so the whole thing is negative. So you're decreasing then again. And I suspect I'll let you work that out. But I suspect that this is going to be positive. This is pi over 2. This is 3 pi over 2. So this is going to be 5 pi over 2. So in here, 2 pi, you can plug in 2 pi. Sine of 2 pi is 0. Cosine of 2 pi is 1. So the whole thing is positive again. There it is. And then it's going to be negative, everything. Sine and cosine are periodic. So you see what's happening. My point is that eventually the function is always negative. So you see here you have a local max. Here you have a local max. Is this local max positive or negative? That's the question. If it's positive and this dipped down below the x-axis, then you'd have another critical point in here. But eventually, the local max has to be negative because this is getting closer and closer to 0. So if anybody's still with us, here's my question. You have a local max right here. So what is G of arctan of 10. Melanie is asking, how are we differentiating the derivative again? Well, we were asking how many critical points f has, which is equivalent to asking how many zeros this function has. I just call this function g. And to study g, you look at its derivative. We would need a calculator for this question, indeed. Yeah, you cannot do this without a calculator. Exactly. We need a calculator to know if it's a positive or negative value. Yeah. I wouldn't expect you to be able to answer that without a calculator. Sod is asking, why can't we apply the squeeze theorem to x sine 1 over x? You can. You can if the question was, what is the limit as x goes to 0? But that wasn't the question. The question was, what is the derivative at 0? Right. So you've seen spend a whole day trying to solve it without a calculator. You really need a calculator here. There's no way around it. But you understand what to do with a calculator now, right? Figure out what this is. If this is bigger than 0, there had to be a root between the two. Now look at this local minimum. If that local minimum is less than 0, there had to be a root between the two. And you keep going. Eventually, the local max has to be negative. Why can't we just calculate g prime equal to 0? We did. We did, and that's what gave us these infinitely many critical numbers. And that's only for half of it. Right? That's only when x is positive. Then you would have to redo an argument when x is negative. The same kind of argument, right? It's going to be the same idea. So I suspect you'll have one here, one there, maybe two more, depending on whether this is positive or not, but probably very few. Right, so either 2 or 4. Eventually, I suspect that the whole thing is going to be negative. Exactly that. All right, I think we may have answered all. All right. All right, one more. Anna wants to do a quick one. Limit as x goes to 9. The square root of x over x minus 9 to the 4. If you just plug in 9, you get 3 over 0, so you know it's some sort of infinity. Normally, you'd want to break it up into left and right-handed limits, but numerator is always positive, denominator is always positive, so the limit is always positive infinity. We're done. All right, that's enough. We've overextended our welcome. Thank you all for coming, folks, and staying this extra hour. If you have last-minute questions, you can email me. I may not respond immediately because I have a few things I have to take care of, but I'll certainly respond by supper time. Good luck. Good luck on your exam, and happy holidays to everyone. I will not be teaching Cal 2 next semester, but if you have questions, feel free to drop by my office. Tuesdays, Thursdays, 2:30 to 4, more or less. I'll be around. You guys have a good one, and I'll see you tomorrow anyways. I'll be there in the gym at some point. All right.